Hey, I'm Pauline.
I'm Lauren.
And I'm Emery. And today we're going to be talking to you about the difference between torque versus torsion. So let's start with torque. What is torque? It is the measure of the twisting force that is applied on an object. It's also known as the moment M. The equation for finding torque is the force applied on an object multiplied by the length from the force to the point that you're measuring. In any sort of statics class, the sum of the moments should always equal 0. Let's look at an example. For this beam right here, as a force may be acting down onto a point, the moment would be acting about that point, causing a rotational force. Looking at some examples over here, such as a wrench, a gear, and a motor shaft, you can see that there are forces acting down along here. But a cleaner way of conveying this in any free body diagram would just be to add a moment or a force about the point that you're rotating. For the wrench, you'll be rotating around the nut or the bolt that you're using the wrench on. For the gear, it'll be acting along a shaft. For the motor shaft, as the motor spins, it's going to be using rotational motion to rotate whatever it's spinning on. Now let's look at a real-world example.
Thanks, Emery. Now I'm going to be explaining what torque is, especially on a door right here. So the axis of rotation right here for this door is right over here, and the door handle is right over here. And when I look at the equation for torque, torque is the force times the distance from the axis of rotation times the sine of the angle of that force. And when I look at this equation further, and I actually kind of put force on one side, so force equals that torque divided by the distance from the axis of rotation times the sine of the angle. What this tells me is that when I increase the distance from the axis of rotation, whether I be pushing it here versus here with a further distance, when I increase r, that makes, when I increase this, that decreases the force that's needed to apply. So that's why when I'm the furthest away from the axis of rotation, it requires a lot less force than over here. It requires a whole lot of pushing force to open that door. And when I'm looking at the angle as well, when sine of 90, that equals 1. And that's the max that sine can equal if you were to look at the sine wave of it as well. So what that means is when you're pushing that force here, that force has to be perpendicular to get the max, the least amount of force applied to open this door. So when I open it perpendicular, it's pretty easy, less force. But if I were to open it like way over here, it's a bit harder, more force. And if I were to open it like along this axis, where the angle is 0 and sine would be 0, then it's not even going to work. I can't even open this door. So that's why when you open a door, you want to be doing it from the furthest distance from the axis of rotation and with an angle perpendicular to the axis along the hinge.
Now let's talk about the difference between torque and torsion. Torsion relates to torque, but it's a different concept. You can think of torsion to torque as you think of force to an axially loaded beam. One is a load, and the other is a loaded case. Torsion is the loaded case in which a moment is acting on a beam about the axis of its length. You can see over here, here is a force acting about on a beam, and here is an axially loaded beam. In the similar case, you can see one point of torque, or a moment, acting about a point, whereas torsion has two moments acting in opposite directions. So this axially loaded case by force creates this stress diagram. Whereas this case with torsion creates a unique state of stress that Pauline will talk about in just a minute.
Thanks, Emery. So regarding torsion, when you were to take a cylinder beam, like a towel per se, and twist it on two sides, I'm going to show you what that surface looks like. So when I draw out the cylinder right here, you can see that end angle, or at least when you slice a piece into it and look at the cross section, there's an angle of twist here, and you can also analyze the shear stress components as well. So when I'm looking at like the surface of this towel and I'm going to twist it, and if I were to draw like lines going perpendicular from this axis, if I were to draw a line up, it actually doesn't change. So if I'm to draw the initial moment the initial just kind of like surface object right here on that, say towel or beam or whatever you are applying a torsion load to, compared to when you twist it and add that torsion element. You can see the difference here is that shear component. These two shears here and here. And when you're to look at the equations, when I'm adding these equations, my assumptions that I have here is that the beam is circular, and it's along the x-section, and then it's a long, thin shaft. It's a homogeneous, isotropic, linear elastic material. There's small deformations. We're not looking at huge deformations here. And the x-section remains planar, as I'm kind of explaining here. There's no axial strain, and the radial lines stay straight, as this example shows of this line staying straight after that load is applied. So when you look at the equations, it kind of goes from like load to stress, strain, and deformation, and they're all related. So first looking at that strain that goes right there, the equation is the rho times the change of the angle of twist, and if you're kind of to look at that here, rho is that distance. If you were to slice it, look at the cross section, rho is that distance from the center to the point that you're analyzing, and so the larger rho is if you were to analyze a point here compared to closer to the center, then you're going to get a larger strain component. So now when we kind of look at the stress, how it relates to load, you get this equation where stress is the torque times that rho value, which is from the center point to whatever kind of distance from the center point, which is rho. It changes depending on what you're calculating, divided by the polar moment of inertia. And what is the polar moment of inertia? It really depends on your material and the shape of it, but also what it's made of. So if it's a solid cylinder all the way filled in, your equation is pi times the radius to the fourth divided by 2. For a hollow one, it's pi times that outer radius to the fourth minus that inner radius to the fourth divided by 2. And when you're calculating the max shear stress, what you do is you look at this diagram here where it shows that shear stress increases when you increase the value of rho, what radius you're looking at. So at the very edge point, at the surface, the max shear stress is the greatest, and it's the torque times the outer radius divided by the polar moment of inertia. And now one more point of this is when you're looking at torsion, you want to calculate that angle of twist, and to calculate the angle of twist, use the torque times the length of your beam. So depending on how long it is, from like here to here, so you add the length in there, times that, or divided by the polar moment of inertia times the shear modulus, and that's the angle of twist. And this sums up torsion. Thanks so much for watching. Now I'm going to send it off to Lauren to give an example problem.
So now that we have an overview, let's take a look at an example problem. A compound shaft consists of two segments. Segment 1 is a solid bronze, G equals 45 GPa shaft with an outside diameter of 80 millimeters, a length L1 equals 780 millimeters, and an allowable shear stress of 65 MPa. Segment 2 is a solid alumina alloy, G equals 26 GPa, shaft with an outside diameter of 95 millimeters, a length L2 equals 620 millimeters, and an allowable shear stress of 40 MPa. The maximum rotation angle at the free end of the compound shaft must be limited to phi of A is less than or equal to 2.5 degrees. Determine the magnitude of the largest torque TA that may be applied at A. So, let's take a look at what's going on in this problem. First of all, we have two members. We have A is the end, B is the center, and C is a rigid wall. We know L1 and L2. We know that a moment is applied to the end. We also know that we have two limiting conditions. First is that the rotation angle at A must be less than or equal to 2.5 degrees, which is equal to 0.0436 radians. For our second limiting conditions, we know that the max allowable shear is going to be 65 MPa in 1. Pardon me. And in 2, 40 megapascals. We also know that G1 is 45 GPa, which is going to be equal to 10 to the 9 pascals per GPa, and then L1 is 780 millimeters, or 0.78 meters. Lastly, we know that diameter of segment 1 is equal to 80 millimeters, or 0.08 meters. For our second member 2, we have that G1 is 26 GPa, which we can convert to pascals. G2. L2 is 620 millimeters, or 62.62 meters. And then D2 is 95 millimeters, or 0.095 meters. As for relevant equations, we're gonna want to know how to calculate the overall rotation angle, which is going to be the sum of rotation angles from both segments. And that would be TI LI over JI GI. It's our first relevant equation. Our next relevant equation is going to be for the polar moment of inertia for a solid cylinder, and that is pi r to the 4 over 2. Next, we want to know how to calculate shear stress, which we know in the general case is equal to the load times the radius at which you're evaluating over the polar moment of inertia, and that the max shear stress occurs at rho equals the radius of the cylinder. So our first step is going to be calculating the internal loads in each member, and this can be done by taking a cut in each and evaluating an equilibrium equation. So if this is member 1, we know we have TA here, and that there must be a force acting here, a moment acting here, which we can call TAV. By equilibrium equations, we know that net moments are 0 equals TA minus TAV, and therefore TAV is equal to TA. We can now take a cross-section through member 2 to determine internal loads in member 2. And again, we have TA acting at the end, and some reaction force acting here, which we will call TBC. Again, we can solve for TBC, and we find that it is equal to TA. Just as a final check, we can also do the full free body diagram, and we know that it's attached to a rigid wall. We have TA at the end and some reaction moment here. Again, TR is going to equal TA. Okay, now that we have our internal forces, we want to figure out which of these conditions get met first. We can start with the overall rotation angle. We have phi A is equal to the sum of the rotation angles of each member, and therefore this is equal to T1 L1 over J1 G1 plus T2 L2 over J2 G2. Now we know that T1 and T2 are going to be equal to TA, so we can say phi of A is equal to TA times L1 over J1 G1 plus L2 over J2 G2. Now we can solve for TA. And plug in numbers, and this gives us 0.0436 radians over L1, which we know is 0.78 meters, over J1, which we can calculate using our polar moment of inertia equation. That'll be pi the radius, which is d1 over 2, or 0.08 meters, over 2 to the 4, again over 2, times G1, which is 45 times 10 to the 9 pascals. And then we have L2 is 0.62 meters over the polar moment of inertia for member 2. Plug in the radius to the 4th over 2 times our G2 shear modulus for member 2, which is 26 times 10 to the 9 pascals. If we calculate this out, it should come to TA max is 5,983.25 Newton meters. So now that we know the max allowable load at the end at A for our first condition, we want to see if the other two conditions have already been met at this max load. So for that, we can use our shear stress equation for max shear stress, which occurs at rho equals R. In 1, we will have TA as calculated down here times the radius of our first member, and that's going to be D1 over 2. And then all of this over J, which is pi 0.08 meters over 2 to the 4th over 2. This should add up to 59.5165 megapascals. We can check 2. And we have TA, which again we're taking from here, times 0.095 meters over 2 over pi times the polar moment of inertia, which is pi times 0.095 meters over 2 to the 4th over 2. And this should equal out to 35.542 megapascals. Our maximum allowable shear stress for segment 1 is 65 megapascals, which this adheres to, and for member 2, 40 megapascals, which this also adheres to. Therefore, our max allowable load is only going to be determined by our first limiting condition of the rotation angle being less than or equal to 2.5 degrees, and we get TA max allowable is 5,983.25 Newton meters.